Struggling with physics? You have come to the right channel. This is Physics is Easy with Mr. Jesse. This tutorial is about a photoelectric effect. To start, let us watch a video presentation on photoelectric effect.
One of the big ideas in physics is that light can behave as waves or particles, and this demonstration of the photoelectric effect is a really great way of introducing that idea. What I've got here is a zinc plate, and if you want the demonstration to work, it's absolutely essential to give it a good scrub on both sides with a bit of iron wool, and that just removes the surface oxide layer. I then place the plate on top of this gold leaf electroscope. I've also got an ordinary desk lamp and a UV lamp. Now, in order for the demonstration to work, this plate has to be negatively charged, and I can do that using the method of charging by induction. Now let me show you that again. I've got a perspex rod here, which I can make positively charged by rubbing with this bit of cloth. I bring the rod close to the plate, touch the plate with my finger, remove my finger, then remove the rod. Now watch what happens when I shine visible light onto the plate. Absolutely nothing. That's actually a really important part of the demonstration. Your students need to notice that with visible light, nothing happens. But watch what happens when I shine ultraviolet light. You can see that the gold leaf immediately starts to fall. And that must mean that the UV light is somehow discharging the electroscope. We know that we started with negative charge on the plate, so the UV light must somehow be releasing the electrons. And the important thing to notice is that it's the frequency of the light that makes a difference. Remember, with a visible light, it doesn't matter how bright it is or how long it shines for, it doesn't release any electrons. Now, this phenomenon cannot be explained using a wave model of light, but we can understand it if we adopt the idea that radiation arrives at the plate as packets of energy, which we can call quanta or photons. A single photon of UV light can release a single electron from the plate. However, a single photon of visible light has less energy and so cannot release an electron. Now, this is a relatively simple demonstration to do, but it took the genius of Albert Einstein to explain what was going on. And it was for that work that he was awarded the 1921 Nobel Prize, not his work on relativity.
To learn about photoelectric effect in detail, click the Edpuzzle icon. For the energy of a photon, recall that E is just equal to hf, or energy of the photon is equal to the Planck's constant, which is h, multiplied by the frequency of light, which is f. Before we solve related problems, let me introduce to you the concept of electron volt. An electron volt is just a unit of energy, and 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. And now let us solve example 7.1. It reads, a sodium surface is illuminated with light of wavelength 0.3 micrometer. And the work function for sodium is 2.46 electron volt. Question A, calculate the energy of each photon in electron volts. Now recall that the energy of a photon E is just equal to hf. However, in this problem, we don't have the frequency of the photon, but we do know from the previous lesson, recall that velocity of a wave is just equal to the wavelength of the wave multiplied by its frequency, and since we're talking about photon, then therefore we're talking about light wave, and the velocity of light wave is c, so we'll have c is equal to lambda multiplied by f, and therefore our frequency can be solved by c which is the speed of light, divided by the wavelength. And we could substitute this equation here in F. So we could substitute it there so that we will have energy is equal to H, and instead of F we will have C over lambda. And now let's substitute our values. Our H, or the Planck's constant, is equal to 6.63 times 10 to the power of negative 34 joules second. And let's no longer write the unit to make the solution much simpler or less parameters. And we have C, which is the speed of light, and that is equal to 3.0 times 10 to the power of 8 meters per second divided by the wavelength, and that is given in the problem to be 0.3 times 10 to the negative 6, since it is in micrometer, and this gives us the energy to be equal to 6.63 times 10 to the power of negative 19, and the unit will be joules. Now, since the question wants us to express the energy of photon in electron volts, then we have to convert this into electron volts by multiplying it with the quantity that we know, and that is 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Then we could cancel the unit of joules, and our answer would be 4.14 electron volts. This is the answer to question A. Having solved A, let us proceed to question B. Question B, calculate the maximum kinetic energy of the ejected photoelectrons. Now we have the equation that the energy of the photon is equal to the work function, or the minimum energy needed to free an electron from a metal surface, plus the kinetic energy. And since question B is asking us to solve for kinetic energy, then we could just manipulate this equation so that we will have kinetic energy is just equal to the energy of the photon minus the work function. And we have solved the energy of the photon in part A, and that is 4.14 electron volt multiplied by the work function, which is 2.46 electron volt, 2.46 electron volt. Then that gives us that the kinetic energy of the ejected photoelectrons is equal to 1.68 electron volts. And we have solved part B. And now let's proceed to part C. Calculate the cutoff wavelength for sodium. Now when we say cutoff wavelength, this is actually the wavelength of the photon that is associated with the smallest amount of energy that is capable of ejecting an electron from the metal surface. So meaning the energy of the photon is just equal to the work function, because if it is just the cutoff wavelength, this means that the kinetic energy of the ejected electrons, or the kinetic energy of the photoelectrons, is equal to 0. So again, cutoff wavelength means that the kinetic energy of the photoelectron is 0. So the electrons are just released or freed from the surface, from the metal surface, but it is not moving. So it just breaks free from the metal surface, and therefore the kinetic energy is equal to 0. Another term for this kind of situation, for cutoff wavelength, this is also related to the threshold frequency. So the same concept, let me write that down. Threshold frequency. Threshold frequency. So in these cases, in both of these cases, kinetic energy is equal to 0. So the kinetic energy of the photo electron. So now let us go back to the original equation. Energy of the photon is equal to the work function minus the kinetic energy. But since the kinetic energy is 0, then therefore we have the energy of the photon is just equal to the work function, and we have the energy of the photon that is equal to HF is equal to the work function, and that is equal to 2.46 electron volt. Now in this case, HF, where the unit of H is joule per second and the unit of frequency is per second, so therefore this energy here is in joule, while the other side still energy but is expressed in electron volts. So it is necessary that we have to convert the work function from electron volts into joules before we solve for the cutoff frequency. And to do that, we would use the value that we know, that 1.6 times 10 to the negative 19 joules is equal to 1 electron volt. So we could cancel the electron volt, and that gives us that the energy, or the work function rather, is just equal to 3.936 times 10 to the power of negative 19 joule. And this is equal to HF. So if the question was asking for the threshold frequency instead of the cutoff wavelength, then we could just divide this side with the H, then we could get the threshold frequency. But since it's asking for the cutoff wavelength, then we need to expand, or we need to express this threshold frequency in terms of cutoff wavelength. Then we will have H frequency, as how we did or solve part A. Frequency is just equal to c, or the speed of light, divided by the cutoff wavelength, and we would call that cutoff wavelength, or lambda c for cutoff wavelength, and that is equal to the work function in joules, which is 3.936 times 10 to the power of negative 19. And then we could manipulate our equation so that we will have the cutoff frequency is equal to Planck's constant multiplied by the wave, the speed of light, divided by the work function in joules, 3.936 times 10 to the power of negative 19. And as we substitute the values for the Planck's constant and the speed of light, we will have the cutoff wavelength to be equal to 5.05 times 10 to the power of negative 7 meters. And therefore, we have solved our problem for part C, which is the cutoff wavelength. And here are the relevant equations and notes on photoelectric effect. And that concludes this tutorial. Once again, always remember, physics is easy with Mr. Jesse.